Hello everyone, this is the video lecture of section 6.6, Applications of Definite Integral in Physics and Engineering. Here we are going to focus on only work, the concept of work here. So, one of the most famous formula in physics is the second law of Newtonian mechanics, Newton's law, which is force, F equals ma, mass and acceleration. All right, Newton's second law of motion. Here, for mass, as international system, international, French actually. So international standard unit. For mass, we use kilogram. Acceleration, meter per second squared. For force, F equals ma, so kilogram times meter per second squared. We call it Newton. Okay? So 1 Newton of force is the force which you can give 1 meter per second square acceleration to 1 kilogram mass. Okay, that's 1 Newton of force. G is gravitational acceleration. It is about 9.8 meter per second square on average, gravitational acceleration. Okay? Now, when you have a mass m near the surface of the Earth, the gravitational pull, the gravitational force exerted on the body by the Earth is called gravitational force. Is exactly this mass times this gravitational acceleration. So for example, if m equals 2 kilogram, the gravitational force exerted on the body by the Earth is what we call the weight of the body. Okay? Then your F sub g, the weight of this one is 2 kilogram times 9.8 meter per second squared. Okay? Which is about 19.6 Newton. All right? So this is in the international standard system. Now there is another system, we call it stupid system, English unit. It's really interesting units. For acceleration, obviously, we use foot per second square, and therefore this is about 32. Gravitational acceleration is about 32 feet per second square. For m, we use mass pound. Mass pound. I'm going to call it sub m, mass pound. 1 mass pound is about 0.454 kilogram. And 1 foot is about 0.305 meter, 30.5 centimeter. Okay? Then, when you have 1 mass pound, and gravitational force on this body, the weight of this one is 1 mass pound times 32 feet per second square. See? That would be the force exerted on this one mass count, mass times acceleration. We define this one as 1 force pound. So I'm going to use this F, 1 force pound. So 1 force pound is the gravitational force or weight of the mass, 1 mass pound, 0.455 kilogram, 454 kilogram. So 1 force pound. So in this unit, force pound actually includes gravitational acceleration on the surface of the Earth, right? It's not good actually. We have some specific Planck acceleration built in the unit of force. But this is English unit, which is about, this is about 4.45 Newton, roughly. Okay? This is 9.8, it's 0.454, so you're going to get this much. Okay? Alright, these are the force, mass, acceleration units. Now, what is work? Done by a constant force. So, if you apply constant force F along this much of distance, force is a vector, displacement is also a vector. Okay. Then we say that work done by the force onto this object is defined as force times distance. If you move in the direction of force, okay, same direction of the force. So work, you use W, force times distance. If the direction of motion, displacement vector is exactly same direction as force vector throughout the work, then it is force times distance. So here, SI unit of work is 1 Newton times 1 meter. 1 Newton meter. And we have a name for it. 1 joule. Okay? 1 joule. 1 Newton meter. So 1 joule is the work done by 1 Newton of force applied to an object over 1 meter. The resulted work done by the force on the object is 1 joule. In English unit, that would be English unit, that would be 1 force pound times 1 foot. That's what we call 1 foot pound, which is about 1.36 joule. Okay? Foot pound, force pound, and 1 foot. So example 1. So in this section, we're going to only study work. A. If you apply 5 Newton all the way here, along 10 meters in the same direction of the force, then resulting work is 5 Newton, 10 meter, 50 Newton meter, which is joule, 50 joule of work done by the force on the object. What if, okay, you apply force to go against the gravitational pull, so that would be, let's say, 15 foot. Let's say m equals 2 mass pounds. In order to lift this one without acceleration slowly up to this, you have to apply the force exactly same as your gravitational pull, which means weight. So applied force is the weight, same as the weight of this. That means 1 mass pound times g, gravitational acceleration is, that's what we call force pound, right? 2 mass pound times g, or 32 foot per second square, that is 2 force pounds. Okay? So you have to apply 2 force pound to move this one slowly, gently, 15 feet higher. Then work will be 2 force pound times 15 feet, 30 foot pounds of work is done. Likewise, if you raise 10 kilogram against the gravity, (5 meters), again, applied force is 10 kilogram G, which is 98 kilometer per square, so 98 Newton. All right. So the work is, so this is the weight. You have to apply the same force as weight to cancel. Net force is 0. So if it was moving, it will be moving 0 acceleration, so constant velocity, slowly pulling up. That would be F, so 98 Newton, right? Force times distance, 98 Newton times 5 meter, 490 Newton meter, so joule. That much of work is done by this force onto this object. Now, so far, we were considering constant force over a distance. What if your force is changing? So, let's say you push some object on the floor. As you move, sometimes you push slow, not so hard. Sometimes you push harder. Over the distance, you have a different strength of force applied. In that case, how do we get to work? Okay? Work done by a varying force. Okay? Let's say you're moving object from, let's say, A to B. You're going to move along this. Your force is F of A here, but any given position, you have a different force at different positions. Okay? At X position, the force is F of X. Alright? Then how do we find the total work done by this varying force? Okay? Alright. So, the way we do this is, first of all, we have to consider approximation. By doing x1, x2, this is xi minus 1, xi. When your object is over here, at that time, the force is xi. Okay? So, what we are going to do is, delta x is b minus a over n. You divide this one into uniform partition. x0 through xn. And we are assuming that this is continuous force at x. It's a force function. It's a function of position. It's continuous or piecewise continuous so that we can integrate. Then let's say Wi is the work done on the interval xi minus 1 to xi. Then total work done from A to B, total work. Then your total work will be just W1 I from 1 through n Wi. See? W1 plus W2 plus all the way to Wi, Wn, right? Work done on the first section, subinterval, and the second subinterval, work over that. Now, here, Wi, when your delta x is very small, or when n is really large, your subinterval is very short. Because we assume the force function is continuous, over a very short distance, your force is almost constant force, right? It doesn't change much because it is continuous function. So, f of x is almost constant on that little small interval. So, it's almost constant, just f of xi, okay? On the whole subinterval, okay? So, your work will be very well approximated by this almost constant force on that interval times the distance, which is xi minus 1, which is delta x, right? Delta x is this length, common length of these subintervals, all right? Almost constant force times the distance of that subinterval. Therefore, your total work is almost very well approximated by this, right? Wi equals this almost. The larger the subdivision, or smaller the delta x, better the approximation. True value will be limit of this expression and goes to infinity. What is it? That's precisely the limit of Riemann's sum. That is definite integral of force function. Force as a function of position. That's how you get the work done by a force function, varying force over some path distance. Okay? Okay, so we extended our work notion to this varying force. Example 2. Now, when a particle located at x meter from the origin, so coordinate x of force of 5 times cosine of x on it. Somehow at any given x, if particles over here somehow, maybe by using magnetic force or electric force, whatever, 5 times cosine of x actually is applied on the particle when the particle is at x. In that case, how much work is done by this force in moving the particle from 0 to pi over 2, about 1.57, let's say, meter. And let's say this is Newton. Force is measured by Newton. The coordinate, the distance, sine the distance is measured by meter. Okay? Then, and also B, how much work is done by the same force in moving the particle from all same as above, from pi over 2 to pi, about 1.57 meter to 3.14 meter. See how much of force work is done by the force in moving the particle from 0 to all the way to pi. Okay, let's do this example. This underscore means same as above. Okay, how much work is done by this force in moving the particles from pi over 2 to pi. That's the force. A, well, our force f of x. Okay. Is 5 cosine of x. So the work, this work is from x runs 0 to pi over 2, 5 cosine of x dx. 5 sine of x, fundamental theorem of calculus, 0 to pi over 2. Sine pi over 2 is 1 and sine of 0 equals 0. 5 times 1, so 5 joule. Okay? B. Well, what about from pi over 2 to pi? Well, 5 sine of x, pi over 2. Sine of pi is 0, sine of pi over 2 is 1. Negative 5 joule. Okay, what does it mean by negative work done? So first of all, positive work done by the force on the object is that from 0 to pi over 2, your force is positive. As you move, your force is in the same direction as your motion, right? So, positive work done by the force means that you put some energy into the particle, right? Work is a transition of energy, transfer of energy from one form to the other. So, if this surface is almost frictionless, that much of work will be transferred to kinetic energy because it's moving fast, right? Accelerating. Okay, and so it's achieved higher speed. So this much of work will be transferred to kinetic energy to the particle. Or if there's some friction, some part of that work will be used to release heat energy from the friction. Now, once you pass pi over 2, as this one keeps moving, your force becomes negative then. Cosine x becomes negative from pi over 2 to pi. So while you're going, your force will start pulling, even though you keep going there. Maybe because of the inertia, just keep going, momentum, and your force is acting opposite direction of your going. So giving negative energy means you're taking off some energy. Some kinetic energy will be taken off, so you slow down. Okay? All right. Now, what is the total work? Sine of x 0 to pi is 0. Or sum of this 5 joule from here to here and then minus 5 joule from here to here, totally 0. So if you go from 0 to pi overall, your force didn't do any work. Overall, the net work done by the force is 0. Okay? Alright. Let me check the recording before we continue. Okay, now let's consider some mass spring system. Let's say you have a ideal spring is fixed at a wall. Okay? Let's say, and then a mass is attached. So, let's say this is neutral position. Neutral position here. Okay? Now, from the neutral position, if you stretch so from the neutral position, I'm going to call it, this one is x equals 0. X much. Okay? Then, in order to do that, you have to apply certain force, right? To cancel this spring force. Alright? Spring force is a restore. If it is an ideal spring, so x positive means stretching, x negative means compressing. Alright? So let's say this is ideal spring. Then F sub x is the force exerted by the spring when the tip, the end of the spring is at x. Okay? So x equals 0 means neutral position. Okay? And then your f of x is the force keeping the spring at s. Therefore, this force will be minus of f sub s, x. Okay? Now, your spring force is minus kx. When you have an ideal spring, this is proportional to the amount of stretch or compress. K is some positive constant. This is called Hooke's law. Ideal spring, Hooke's law. Okay? So K is a spring constant. Spring constant. Or stiffness of the spring. Larger the K, greater force will be exerted because it's stiff. Alright? So the force, keeping force at x will be minus minus of kx then, all right? X is positive, you have to stretch. Then this to the right is a positive direction. If x is negative, you have to the left, compress, right? So thanks to the Hooke's law, you have this for ideal spring. Now, example 3. A force 20 Newton is required to hold a spring that has been stretched from its natural length 30 centimeter to a length 40 centimeter. So the original length of the spring is 30 centimeter. In order to stretch from original length 30 to 40, so you have 10 centimeter net change from the neutral position, 10 centimeter. In order to keep it that way, you're required to exert 20 Newton. Okay? In that case, how much work is done in stretching the spring from 40 centimeter to 60 centimeter? How much work is done, obviously, by this force, by the force on the spring or object attached to the spring in stretching the spring from 40 to 60 centimeter. First of all, we have to find spring constant from the first information. So, force equals 20 Newton when x is what? 40 centimeter minus 30 centimeter. Since 30 centimeters x equals 0. 10 centimeter or 0.1 meter. That's the x. When x coordinate is 0.1 meter. X equals 0 means neutral position. You have 20 Newton from F equals kx. 20 Newton equals k times 0.1. Therefore, k will be 200. The unit is Newton per meter, obviously. Okay? So, your f of x is 200 times x. K equals 200. Okay? Then how do we get the work? 40 centimeter means x equals 0.1 meter, right? 60 means x equals 0.3 meter, because 30 to 60 centimeters, 30 centimeter, or 0.3 meter. So, they are asking the work done by the same force from 0.1 to 0.3 f of x dx, right? The definition, the work. So that is 0.1 to 0.3, 200 x dx. That would be 100 times x squared from 0.1 to 0.3, 0.09 minus 0.01, 0.08 times 100 is 8 joule. Much of work was done by the force, stretching force, to the spring. Okay? All right. Then last example of the section is if the work required to stretch a spring 2 foot beyond its natural length is 12 foot-pounds. So there is a spring that when you stretch 2 feet from that natural length, 2 feet, you realize that you are doing this much work, 12 foot-pounds much of work to the spring. Okay? Then, how much work is needed to stretch the spring 18 inches beyond its natural length? Not 2 feet, but just 18 inches, 1.5 feet. Okay? Again, we have to find K value, right? Spring case. So f of x is, again, we are assuming Hooke's law, ideal spring. What we got was the work when x is from the natural length to 2. When x changes from 0 to 2. That was 12. That's what it says, right? This is k over 2x squared, 0 to 2, 4. So it is 2k equals 12. So k equals 6. So the first sentence, first part of the problem, will give us a clue about what spring constant k is. In this case, 6. So your force function is 6x. Now, 18 inches is 1.5 feet, or 3 over 2. Okay? So the work done during the process of stretching from the original length, which is x equals 0, to this much, 3 over 2. K, f of x, 6x. Alright? Then 3 times x squared, 0 to 3 over 2, 9 over 4. Right? Square. So 27 over 4, or 6.75 foot-pounds. Okay? The unit, English unit of work. So, in both cases, either they give you force should be exerted, the amount of force exerted to keep spring at certain distance, so that you can get K, or they give you how much work is done by stretching from the original length to certain length. And from here you have to find K value, either from the work formula you find K, or force, Hooke's law, you find K. Alright? Okay, so out of all these applications, I chose work to cover, because in calculus 3, when you do line integral of a vector field, the most important example of that case is line integral force field along the. So the line integral of a force field will give you work done by that force field. Like if you have electrostatic force field and some charges moving from here to here are under certain routes, then how do we get work done by the force field? from here to here along that path. Then you have to do line integral of that force vector field. So, my opinion, you have to, that is the most important example or motivation. Maybe the reason why we invented the concept of actual integration to begin with. So that's why I chose to cover this out of all these different applications. Hopefully this one is good enough for students who have not taken serious physics yet. Okay, all right. That's the end of section 6.6, and I will see you next time. Bye.